welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Arabic College, University of Delhi. And previously we have seen the topic of CPU synchronization, or we can say we have seen the brief introduction to CPU synchronization module of operating system concept series, and today we are going to take that further. So welcome to the second part of this second part of this module, which is CPU synchronization. Now we have seen that in order to we can say in order to have a stabilized multiprogramming system, we need to have CPU scheduling as its integral part. Now CPU scheduling, if we talk about the types of scheduling, there are mainly two types of CPU scheduling methods. One is the preemptive scheduling, another one is the non-preemptive scheduling. So preemptive scheduling is used when a process switches from running state to ready state, or from waiting state to the ready state. That means there is, we can say, there is no jumping. Now what I mean by this jumping, I will be explaining in a little while. So basically, when a process switches from running state to a ready state, or from waiting state to a ready state, so either from a waiting queue or from a running queue, the process is going to take charge of CPU. That is what it is. While non-preemptive scheduling, if we say, is non-preemptive scheduling is used when a process terminates, or when a process switches from running state to waiting state. So we will be exploring more about this CPU scheduling methods, which are preemptive and non-preemptive scheduling. So in non-preemptive scheduling, new processes are executed only after the current process has completed its execution. So the current process, which is kind of holding the resource of CPU, which is, we can say, CPU cycles, or which is holding the CPU time, it will keep on holding its till its state changes to terminated, or it is pushed to the process waiting state. So either the kind of, we can say, your process has completed its termination, completed its execution, and now it's going to be terminated, or because of any reason it is going to be terminated, or it is being pushed to the waiting state. While if we another state, if we see that if a process is currently being executed by CPU, it is not interrupted till it is completed. This is non-preemptive scheduling. That means we are not going to preempt the process which is already going on, which is already running. Once the process has completed its execution, the processor picks the next process from the ready queue, or the next process from the ready queue is being assigned to the processor, and this ready queue is nothing but the queue in which all the processes which are ready to get the control of CPU are stored. So the process has completed the execution, and a new process from the ready queue will be taken, and it's kind of given to the CPU. So here, if you can see, if we try to understand this non-preemptive scheduling, what is happening here is we have four processes as named as P0, P1, P2 and P3, and there is kind of arrival time. So arrival time is at 2, arrival time is at 3, then arrival time is at 0, and the arrival time is at 1. And there is the CPU burst time. So CPU burst time, as we have seen in our previous lecture, what amount of time of CPU they are looking for. So that is given in milliseconds. So process P0 is looking for CPU for 8 seconds, P1 is requiring CPU for 6 seconds, then P2 is requiring 6 for 9 seconds, and P3 is requiring CPU for 4 seconds. Now if we see the arrival time here, the arrival time, the P2 is having the earliest arrival time, which arrives at 0, kind of we can say 0 seconds or something. it has arrived at the time 0. So this P2 has been given the processor. Now P2 needs the processor for 9 seconds. So the Q which is given, which is given under the table, if you can see on the screen. So at 0th second, P2 has come up, started with its kind of CPU burst, or started it with execution, and till 9 seconds, because that was the requirement of P2, 9 milliseconds of CPU burst time it was looking for. So till 9 seconds P2 was executing. Then after this we have P3 which arrived at first second, or we can say second 1. Then P3 has taken the control and used the CPU for 4 seconds. So 9 plus 4 gives you 13. So till 13 unit of time instances, or till 13th second, 13 millisecond we can say, it is P3 which is kind of in execution after P2. Then comes to P0, because that is the process which has come up after the P3. Now when I am saying come up after the P3, that means that is essentially, you can see the arrival time. Arrival time of P2 is 0, arrival time of P3 is 1, then arrival time of P0 is 2, and the arrival time of P1 is 3. So initially it was the P2 which came up, then it was P3, and then it was P0, and whatever time of CPU burst they have kind of asked for are given to them. So P2 has been given a CPU burst of 9 millisecond, followed by P3 which has been given the CPU burst of 4 seconds, followed by P0 which has been given the CPU burst of 8 seconds. So 13 plus 8 makes it 21, and after P0 it will be P1 in the queue which has been given the CPU burst of 6 seconds, making a total of 21 milliseconds in all for execution of all the 4 processes. Now what is happening here? Initially when P2 was execution, P3 has arrived, P1 has arrived, and P0 also has arrived, but they don't preempt P2. They will not we can say disturb P2, or they will not take the control of CPU from P2 till P2 complete till P2 has completed its we can say execution, or till P2 has completed its CPU burst time. Then comes P3. Now why P3 has been taken here? For the simple reason that P3 has come up at the second number 1, or in that was second to come up in the queue at time instance 1. Then P3 has given 4 seconds of CPU time. No one preempted it, or no one taken the control of CPU. Similarly, that goes with P0 and P1. So this kind of CPU scheduling is, we can say, is non-preemptive scheduling, in which all the processes were executed in the order. Here we have seen that the processes were executed in the order of which they appeared, and no process was interrupted by another. So if no process was interrupted by another, this is, we can say, it's a non-preemptive scheduling. And examples of non-preemptive scheduling algorithms are SJF, which is shortest job first non-preemptive version I am talking about, and the priority scheduling non-preemptive version. Now what is this shortest job first and priority scheduling? That we will be covering later. Now for example, let's say instead of this non-preemptive scheduling here, let's say we have preemptive scheduling. So preemptive scheduling, we can understand it by this: it takes into consideration the fact that some processes could have a higher priority and they must be executed before the processes which are on the lower priority. Also, one policy here is the CPU resources are allocated to a process for only a limited period of time and then these resources are taken back and assigned to another process, which is kind of which is next in the execution. But in non-preemptive scheduling, once you have allotted the CPU resources to one particular job, that will not be taken back unless that job has completed its execution. So, but here in case of preemptive scheduling, one process which is having a higher priority can preempt the process which is going on and is having lower priority. So, for example, a lower priority process is having the control of CPU, and there comes a higher priority job. That higher priority job is going to take the control or take the charge of CPU from the lower priority job, and will execute itself, or the execution of higher priority job will take place. So, this is what you called as preemptive scheduling, in which the process, if the process was yet to complete its execution, it can placed back in the ready state where it will remain till it get a chance to execute once again. While in the non-preemptive scheduling, non-preemptive type of scheduling, this does not happen. So, in non-preemptive type of scheduling, the processes were executed in the order of which they appeared, and none of the processes was interrupted by another process, while in the preemptive scheduling, one process which is maybe of lower priority can be preempted by a process of higher priority. So, these are basically, we can say, two types of scheduling, two types of CPU scheduling. One is preemptive and another one is non-preemptive. So, with this background of types of scheduling, let us see what are the situations in which CPU scheduling is required, or what are the situations of CPU scheduling. So, there can be 4 situations of CPU scheduling. First is when a process switches from a running state to a waiting state. So, for example, a process is in a running state, that means it is having CPU and the execution is going on, and somehow it is in the need of maybe an input output burst or something of that sort, and the running state, from the running state it is being switched to the waiting state. Another idea could be when a process switches from the running state to the ready state, for example, when the interrupt occurs. So, if there is an interrupt occurring, then the process from the running state will be taken up, and it is kind of, we can say, it will join the ready queue, and after the termination of that interrupt, or after the completion of interrupt, it can resume. Or the third situation of the CPU scheduling could be when a process switches from a waiting state to the ready state. That means the process was in the waiting queue, or was in the waiting state, and it was waiting for completion of an input output activity, and now with the completion of that input output activity, it will switch to the ready state. That means now it is ready to take up the control of CPU. And the fourth one is when a process is terminated. A process is going on and it has completed its execution, and somehow it is terminated. So, these 4 are the situations when we need to schedule the CPU, or we can say all these 4 are the situations of CPU scheduling. That means when a process comes from running to waiting state looking for an input output activity, then one is when an interrupt occurs. So, from running it will go to the ready state. Third one is when a process switches from waiting state to the ready state. That means the activity it was waiting for, or maybe an input output activity has been completed, and now it is ready to take the control of CPU. And the fourth one is when a process terminates. All these are the situations when you need to schedule the CPU. That means the control here, we can say, is changing. So, we can see that if we are talking about situation number 1 and situation number 4, so these are when a process switches from running state to waiting state and when a process terminates. We don't have any choice here in order to make a decision. But if we talk about the situation number 2nd and 3rd, which is situation 2 and 3, that means when a process switches from running state to ready state and when a process switches from waiting state to ready state. So here we can say we have a choice in these two conditions, that which particular job is to be or which particular process is to be given the control of CPU. So in case of condition 4, if we opt to make the choice of scheduling only if a process terminates, what is the condition 4, or if the current process execution is waiting for input output, then we can say our scheduling is non-preemptive. That means in case of 1 and 4, the scheduling is non-preemptive. That means whichever process was taking the CPU or was having the CPU, these are not preempted. These processes or that particular process which was handling the CPU was either being terminated or has changed its state from running to waiting, and we need not to have any kind of, we can say, we have not forced the process to release the control of CPU. So here we can say that the scheduling is non-preemptive. Now in case of the option number 2nd and option number 3rd, which was the occurrence of the interrupt and switching completion of an input output in which process switches from waiting to the ready state, these are the two decisions. So in which if we make the scheduling decisions in the other conditions like 2 and 3, we can say that our scheduling process is preemptive. That means obviously in case of we can say interrupt, it is something which is done by force. That means if we see from a process point of view, the process was taking the control of the process has already taken the control of CPU and was in execution mode. Suddenly an interrupts occur, we have taken the control of CPU from that particular process and put it in the ready queue, and then we the CPU is now busy in serving the interrupt. So what have we done? Actually we have taken the control of CPU forcefully. So in 2nd and 3rd situation, if we are making scheduling decisions in these conditions, we will be saying that the scheduling process is preemptive, while the 1st and the 4th one, in which the process is actually terminating or moving to the waiting state, in which we are not forcing the process to release the control of CPU. It is by the process choice or it is by the circumstances of the process that it is kind of releasing the CPU. So that's why non-preemptive, and 2nd and 3rd are actually preemptive. So if we see what are the policies which comes under preemptive and what are the policies which comes under non-preemptive, here we have a kind of a chart like figure on the screen. If you can see here, we have preemptive scheduling algorithm as priority scheduling, longest remaining job first, SJF, which is shortest job first, and we have a round robin policy. All these policies we will be kind of studying in detail in our upcoming lectures. So as far so here we will be just going through the names. And if we talk about non-preemptive scheduling algorithms, these are shortest job first. So please notice that shortest job first, which is SJF, is in the section of preemptive as well as in the section of non-preemptive as well. We can have a version of shortest job first which is non-preemptive. We can also have a version of shortest job first which is preemptive. So apart from the shortest job first, in the category of non-preemptive we have longest job first also, then SCFS we have, then we have highest response ratio next. So these are the policies or these are the names of the scheduling algorithm which we will be going through in detail. and the figure shows that which particular scheduling algorithm is falling under which particular category, whether it is falling under the type of preemptive scheduling or it is falling under the type of non-preemptive scheduling. Then in non-preemptive scheduling, as we have seen that once CPU has been allocated to a process, the process is going to CPU until it releases the CPU either by terminating or by switching to a waiting state, that is 1 and 4. And now what are the operating systems which are using this type of scheduling is, it was used by Microsoft Windows 3.x. So if you remember, there was a very old version of Microsoft or we can say earlier versions of Microsoft Windows which are named as Windows 3.x. Then Windows 95 was introduced in the market, that also have that Windows 95 introduced preemptive scheduling, and all the subsequent versions of Windows operating system are using preemptive scheduling. Before Windows 95, which was MS Windows 3.x, it was using non-preemptive scheduling. Then if we can see some other operating systems like Mac OS operating system also uses preemptive scheduling, while the previous version of Mac operating systems relied on one more type of scheduling, which is cooperative scheduling. So Windows earlier was using non-preemptive, then it switched to the preemptive, while this Mac OS is using preemptive and the earlier it was using cooperative. If you can see in the previous lecture, if you recall, in terms of when I was explaining process synchronization, we have gone through one particular condition, or we have explained one scenario which was race condition. So race condition is something is occurring when a data which is being shared among several processes is more than one processes are kind of, we can say, accessing the data same time, and that too kind of in a write mode. So we can say the preemptive scheduling can result in the race condition when data is shared among several processes. So let's say we have two processes which share the data. So while one process is updating the data, it is preempted because the scheduling is preemptive. It is preempted, and why it is preempted? Second job has come, and maybe second job is having the higher priority. So the first one is preempted, so that the second can make its way, and so that the second can run. And now the second process is going to read that particular data which was being updated by the first process. And now that particular data will, there is a high possibility that this particular data will be in an inconsistent state, because when this was being updated at that particular point of time, we can say this, the process has been preempted, or the first process has been forced to leave the control of CPU. So here we can say we may arrive race condition with the situation of preemptive scheduling. Now along with this preemptive and non-preemptive scheduling, we have one more component which is majorly involved in CPU scheduling, and that component is dispatcher, or basically it is a module that gives control of the CPU to the process selected by the short-term scheduler. So the job of the short-term scheduler is to select a particular process. Now who is going to hand over the control of CPU to that particular process? It is the module of the dispatcher. So this dispatcher involves what all? So this dispatcher involves the switching context, it involves the switching to the user mode. It also involves the jumping to the proper location in the user program to restart that particular program, and the we can say constraint here with the dispatcher should be as it is performing the context switch, this should be as fast as possible, because the context switch is in the hand of dispatcher. The time it takes for the dispatcher to stop one process and start another one is known as dispatch latency. So we have one process which is going on, So dispatcher is going to stop that particular process, take another process which has been already selected by short term scheduler. After taking that particular process, it is going to give the control of CPU to that particular process. So this particular time, which is the duration between stopping of one process and starting another one, is known as dispatch latency. So if we talk about this dispatcher, we have one more term which is heavily involved in the CPU scheduling process, and that term is the interval timer. So interval timer, or we can say it is timer interruption, it is a method that is closely related to preemption model of CPU scheduling. When a certain process gets the CPU allocation, a timer may be set to a specific interval. Both the timer interruption and the preemption forces a process to return the CPU even before its CPU burst is complete. So even the process is looking for more CPU burst, or processes requiring more CPU time. Either it is timer interruption, or it is the forceful interruption of preemption model. The process is required to return the CPU, and most of the multi-programmed operating system uses some of the timer to prevent a process from tying up the system, or prevent the process from eating up the system forever, so that other processes should not land up in the state of starvation. So here if we can see in this lecture what we have seen, we have started with two types of scheduling, which is the preemptive scheduling and non-preemptive scheduling. After the understanding the concept of preemptive and non-preemptive scheduling, we have seen what is the what are the situation in which your preemptive scheduling can work, and what are the situation in which your non-preemptive scheduling is going to work, that we have seen. And apart from that, we have also seen what all short scheduling algorithms will fall under which type of the category of scheduling algorithm. Also we have seen two more concepts which are very important in terms of CPU scheduling, and these are interval timer and the dispatcher. Here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed it. Thank you for a patient hearing.